You're building a cookie tin. It has to hold a fixed amount, and metal costs money, so is there O-N-E best radius using the least metal? Once it's built and filling, how fast is the level rising right now? And if the finished radius is off by a couple of millimeters, how much extra metal did that cost? Keep this tin in your head. You already found this number back in 2.2. Di/dx at one single point is the exact steepness there. Here's the new step. That number becomes an actual straight line through the point, the tangent. It's the m in a straight line equation you've known for years. Y minus y1 equals m times x minus x1. Plug in the point and the slope you already have, and you've written down the actual tangent line. Guess if the tangent slope is 4, what's the normals? Not -4, think perpendicular. -1/4. Tangent slope times normal slope always makes -1. Once you solve for x, go back to the original curve for y, never the derivative. A common slip. You have both tools. 2.2 finds a flat spot, 2.3 finds max or min. New step, turn this into O-N-E variable. This tin has two free numbers, R and H, and infinitely many pairs hold the same volume. Use that volume as a constraint to write H in terms of R. Substitute it in, and H disappears one curve, in R alone, ready for every tool you own. Differentiate, set to 0, solve for R. Then substitute back into the original, not the derivative. Watch R slide. The metal drops, bottoms out, then climbs. That bottom is the least metal this tin can use. Question one of our hook answered. Two things change at once. Volume depends on radius, and radius is changing with time too. Guess before I show you. To link the two rates, do we multiply or divide one by the other? We multiply through the chain. V depends on R times R depends on T. Question 2 answered. Forget time. Picture X nudging just a tiny bit, once, like this tin's radius slipping by a couple of millimeters. Zoom in on any curve, and it stops looking curved, it looks straight, like it's tangent. The change in y is the slope times that nudge in x. Quick guess. If the radius shrinks, is the nudge positive or negative? Negative always match the sign to what's really happening. Here's the chant, rate needs a ticking clock. Small change is just a nudge, no time at all. Question 3 answered. That's the extra metal the slip cost. Back to our tin. The best radius using the least metal, that's turning points at work. How fast it's filling, that's related rates. A tiny sizing slip, that's a small change. 3 questions, 1 idea, di by dx used 3 ways. Curve y equals x squared plus 2x minus 5. Tangent at x equals 1, then the normal. Differentiate. Di over dx equals 2x plus 2. Using the original curve at x equals 1, y equals negative 2. Substitute x equals 1. Gradient for the number from the tangent beat. Plug the point and gradient into y minus y1 equals m times x minus x1. Y equals 4x minus 6. Flip to the perpendicular gradient, negative 1 over 4. Same point, never the derivative. Expand the bracket first. Y plus 2 equals negative 1/4 x plus 1/4. Multiply every term by 4 to clear the fraction, then collect everything on one side. X plus 4y plus 7 equals 0. Tangent, y equals 4x minus 6. Normal, x plus 4y plus 7 equals 0. An open-top cylinder, volume 64 pi. 4 parts, area, minimum, rate, small change. This is the S.A.M.E tin, open top, just the base plus the curved side. The volume is the constraint, like the two sliders collapsing to 1. H equals 64 over r squared. Substitute H in. 2 times 64 is 128, and 1r on top cancels 1r on the bottom, leaving just r underneath. So it equals pi r squared plus 128 pi over r. That's part A. Differentiate, set it to 0, then multiply through by r squared to clear the fraction. 2r cubed equals 128, so r cubed equals 64. Take the cube root of both sides. R equals the cube root of 64, which is 4. Put r equals 4 back into the original formula. Minimum area 48 pi. The second derivative stays positive, a genuine minimum. That's part B. A smaller prototype at r equals 2, a different radius, growing at 0.05 centimeters per second. Chain the rates. d by dt equals d by doctor times doctor by dt, negative 1.4 pi. Real negative before the true minimum. The radius is corrected from 2 to 1, 98. Just a nudge, delta r equals negative 0, 0.2. Multiply by that d by doctor. Rate needs a clock, this doesn't. Delta is about 0.56 pi, an increase. A, pi r squared plus 128 pi over r. B, r equals 4, area 48 pi. C, negative 1.4 pi per second. D, about 0.56 pi, an increase. Radius 4 for the least metal, 1.4 pi per second filling. A 0.02 slip costing 0.56 pi, all from di by dx. Reach for tangent and normal when a curve gives a point. Reach for turning points for the b, e, s, t, or least value. One variable, differentiate, substitute into the original formula. Reach for chain rule rates with t, I, m, e, and small change for a nudge with none.